In this new exercise, we have to sum this series, right? There's a difference with respect to previous exercises in which this is actually a series, which means that the upper limit here is infinity. So it doesn't depend on the parameters of which this expression depend on. So for instance, this expression after we perform the summation will depend on this integer, this natural number n, and on the parameter a, which is a real parameter, right? So this will be a number cn different for every n, which is a function of the parameter a here. Well, this is a disadvantage, is a disadvantage and an advantage at the same time. It's a disadvantage because it's an infinite sum, so if we want to calculate this numerically, then we have either to add infinitely many terms of, or devise a criterion to truncate this series at some point, or, and it's an advantage because this limit here does not depend on the parameters of which this expression depend on. So there will be no problem in interchanging summations, which is what we have to do whenever we try to figure out what this is, applying generating functions, right? We normally extend also the lower limit to minus infinity, but in this case this is forbidden because here we have k in the denominator, so k equal to 0 is not even defined, so we better leave it like this. There's not really much of a problem because 1 also is a constant, it doesn't depend on n or a, so it won't be a problem to interchange summation. So as usual, what we're going to do is to introduce the generating function fc, which is the sum from n equal to 1, because n runs from 1 to infinity, 1 to infinity, and then we put cn. Forget about this a. I mean, we know this implicitly depends on a, but we're going to just ignore that in the notation. And here we have set to the n, right? So this is the summation we have to do. We have to determine this function f, and then afterwards, if possible, expand it to find an explicit form for this, right? Will be the sum of this series. Okay, so we perform this sum. So what we have here is f is equal to the sum from n1 to infinity, and we write set to the n, and then we write cn, which is this expression, so the sum from k1 to infinity, n plus k minus 1 over 2k minus 1, a minus 1, 2k, a n minus k, and down here we have k, right? And as we have done in several cases now, you interchange the summation in these summations. The two summations you have to perform. So we first sum on k, right, and later in n. But we're going to get out everything that does not depend on n, right? So for instance, this factor here or this k, okay? So we can put it here outside the sum on n, and then we sum on n 1 to infinity, and we put the rest. So this combinatorial number, n plus k minus 1, down here 2k minus 1, right? Then we have a n minus k, and then we have set to the n. All right. Now focus on this combinatorial number here. This combinatorial number is 0 if n plus k minus 1 is smaller than 2k minus 1, which means n smaller than k. So that means that for every index n running from 1 up to k, excluding k, all contributions to this sum will be 0. So we can perfectly well start at k without changing anything, right? Because all the terms that we are discarding in doing this are all 0. All right. Then the next step is to change the variable in this summation, right? So what we're going to do is to introduce a new variable, which is n is going to be k plus j. So as j goes from 0 to infinity, n will run from k to infinity, which is the sum that we have here. So we transform this sum. Okay, we copy the first one, right? A minus 1 to 2k over k. And we transform this sum into the sum on j from 0 to infinity. And then we transform this by substituting n by this here, right? So we have j plus 2k minus 1. And down here, we can just copy 2k minus 1, or using the duality of the combinatorial numbers, write j there, right? Then we have n minus k, which is simply j. So we have a j. And then we have n, which is set to k plus j. All right? So we have a set to k, so we can split this in two. Set to k times set to j. And now we can take this out here, right? Because this does not depend on j. So we just copy this, right? We're going to copy this expression. Well, actually, better than that, I'm just going to leave here set to j and put here set to k. All right? Okay, let's focus now on this summation here, right? What we have is this. We have the sum from 0 to infinity, and we have j plus a number, which is 2k minus 1, j here, and then we have a set to the power j. And this is a sum that we can recognize. This is just 1 over 1 minus the variable, a set to the power j, right? Sorry, to the power j, no. To the power 1 unit more than this number here, so to the power 2k. So all we have to do is to substitute this back here, and then we have the sum from k1 to infinity. Then we have a minus 1 to k set k, and then we have 1 minus a set to k, and here we have 1 over k, right? This factor 1 over k that we have there. Okay, this is a much simpler expression, but we can still transform that. If we write the following, that's the sum from 1 to infinity, then we have 1 over k, and then we have a single variable, which is a minus 1 squared times z divided by 1 minus az squared, right, to the power k. Okay, so all these factors are to the power k. So what we have is something of this form. So from k1 to infinity, x to k over k. X is this factor here, right? This is x. So this, if you look at the table of expansions, this is minus the logarithm of 1 minus x, right? So what we have here is the sum, is minus the logarithm of 1 minus a minus 1 squared z over 1 minus az squared. Okay, right. We're going now to simplify this a little bit, because in this form it is very difficult to make any expansion in powers of z, right? So let me try to simplify this a little bit if possible. So we have this term there, and that is equal to, we reduce to a common denominator, so we have 1 minus a z squared minus a minus 1 square z, right? And then in the denominator we have 1 minus a z squared. Okay, so let me expand these two binomials, right? And then we have we will have 1 minus 2az plus a squared z squared minus a squared z plus 2az minus z, right? And down here we have 1 minus az squared. Okay, this cancels with this, okay? And then we have 1 plus a squared z squared minus a squared z, right? Minus z here. 1 minus a z squared. Okay, look at the numerator here. We can write, of course, 1 minus z. And then we have two other terms for which this is a common factor. So we write a squared z times z minus 1, right? Because you see there's a squared z squared here, so that's the first term, and there's minus a squared z. And down here we have 1 minus a z squared. And you see this factor is equal to this one with the opposite sign, so actually the numerator has this factorized form, square z, right? Over 1 minus a z squared. Okay, this is a much better way for introducing here, because it's got factors and we have a logarithm here, and the logarithm of products is the sum of logarithms. So what we have here is that the generating function is equal to minus the logarithm of this expression, which is minus the logarithm of 1 minus z, minus the logarithm of 1 minus a squared z, plus twice the logarithm of 1 minus a z, right? Twice because there is a square here, okay? So it's this sum of logarithms, or this combination, linear combination of logarithms, and now each one of these logarithms can be expanded using this expansion that we have up here, right? So in the first case, z is x, in the second case, a squared z is x, and here az is x. So we just substitute there. Now we have the following: we have the sum from 1 to infinity, right? And from this we have z to the n over n. Then from this one here we have a squared, well, a to n z to the n over n. And from this one here we have 2 times a n z n over n. And we can factor out 1 z to the n, right? So this factor here, and this factor here. Okay, write the z to the n here. Okay. And what we have in front of it is just Cn of a. It's exactly the sum that we were looking for, right? As a matter of fact, you can simplify it even more, because this is equal to 1 plus 2an plus a to n, right, over n, and this is equal to, you see this is a perfect square, is 1 plus an squared over n. So it turns out that such a complicated series that we had at the beginning simply becomes, well, simply has this small form from the this very simple form. Oh, sorry, there's a mistake here. There's a minus here because I forgot that there's a plus here, so it's the opposite sign. So this is a minus, so that means that there's a minus here, right? There's a minus here, and that this is a minus. So we can actually write it like this: an minus 1 to the square. All right. But again, what I was saying is, we started off from this very complicated expression for a series. Hard to believe that this can be summed at all. And by this technique, we reduce this complicated expression to just this very simple expression here. There's a major achievement that you can do with using generating functions. It doesn't mean that it always works, but sometimes it does, and when it does, it can produce simple expressions for complicated sums.